Picture an atom in your head. You're likely imagining a tiny solar system, a dense core in the middle, surrounded by planetary electron orbits zooming around in perfect, predictable circles. You see this image everywhere because explaining the actual physics is a slow, difficult process. Educational channels often choose to teach this outdated model because it fits into a shorter runtime. This creates what I call oversimplification debt. By prioritizing quick dopamine hits over the actual science, these videos provide the illusion of learning without the substance to back it up. This matters because the solar system model cannot explain how atoms actually stick together. If electrons really moved in simple circles, the chemical bonds that hold your DNA or the water you drink together would be mathematically impossible. In our daily lives, we can measure both the position and the speed of a fired baseball at the same time. But at the subatomic scale, those rules of measurement disappear. This is Werner Heisenberg. He discovered a law of the universe that forbids knowing everything about a particle at once, the Heisenberg Uncertainty Principle. The paradox is simple. The more precisely we measure an electron's speed, the less we can know about its exact location in space. This destroys the very idea of an orbit. To have a predictable path, you must know exactly where the particle is and where it's going, which this principle makes physically impossible. If the building blocks of our world cannot travel in predictable circles, then the foundational model we've all been taught is broken. Erwin Schrödinger realized that instead of acting like distinct little planets, electrons behave like waves. He developed an equation that replaces the planetary model with a three-dimensional probability cloud. In this state, called superposition, the electron doesn't inhabit one single spot. Until it is measured, it is effectively everywhere inside that cloud at once. This raises a structural question. If electrons are overlapping fuzzy waves of probability, how do they stay organized around a nucleus without crashing into each other? To keep those clouds from collapsing, the universe relies on a rigid set of architectural rules. The universe manages this through 4 quantum numbers. Together, they act like a unique barcode for every single electron, forming a strict seating chart. The first number represents the main energy shell, like a hotel floor. The second and third numbers define the specific shapes and orientations of subshells on that floor, the spherical S, dumbbell-shaped P, and the abstract balloon animal D and F subshells. This is Wolfgang Pauli, who defined the limit for how many electrons can fit inside those shapes, the Pauli exclusion principle. Because of a fourth number, electron spin, every individual orbital shape is strictly capped at a maximum of 2 electrons. These mathematical limitations are what prevent chaotic probability waves from collapsing, resulting in the stable matter we see every day. As atoms grow, these probability clouds stack on top of each other in a specific order called the Ausbau principle. This chart shows how those orbital limits dictate the entire periodic table. Because an S subshell holds 2 electrons, the S block on the left is exactly 2 columns wide. Because the P subshell holds 6, the P block is 6 columns wide. This geometry is why elements react the way they do. The shapes of these clouds determine how atoms share electrons and form the molecules that make life possible. The solar system model is easy to understand, but it hides the mathematical reality of how our universe is built. Rushed learning might give you a quick answer, but it leaves you blind to the mechanics that actually drive chemistry and biology. Taking the time to understand this probability-based reality reveals why the world around you is solid and stable. By moving past the convenient fiction of the solar system atom, we can finally see the rules that govern the physical world.